Okay, I think we can start now. Okay, we continue with harmonically excited vibration, a system subjected to base motion. Any question from previous week?
No, say.
Okay, this week we will try to cover the response of a damped system under the harmonic motion of the base, the response of a damped system under rotating ambulance, forced vibration with column damping, forced vibration with hysteresis damping, and self-excitation and stability analysis. Here we assume a system with single degree of freedom. The system includes of a mass, a spring, and a damper subjected to the base motion. And the base motion is a harmonic motion, as you can see here. This is the, as I explained in previous chapter, I explained that the simplest form of the excitation is always a harmonic excitation, because we can easily find the response by using the theory of the ODEs. So here again, we start with a harmonic base excitation. We can assume that yt, or the motion of the base, is equal to uppercase y sine omega t. So we can extract the equation of motion for this system. We will have, if you plot the free body diagram for this system, if you plot the free body diagram, we will have one force due to the spring. When this mass M is going up, we will have one force in this direction. In downward direction, and the value of this force is K times by X minus Y, because both edges of this spring is moving. So when this mass M is going up, this edge at this point will go up, and also we will have one motion of this point, the other edge, which is called Y. The displacement of this point, the upper edge, is called X according to the degree of freedom for this system, and the displacement of the lower edge is called Y, which is the base excitation. So the total displacement of this spring is X minus Y, or the difference between the upper edge displacement and lower edge displacement, which is called X and Y respectively. For the damper, we have the same scenario. Again, it will be C times by the velocity of the damper. Again, we have one velocity at this point, which is called X dot, and one velocity at the lower edge point, which is called Y dot. So the force in the damper, sorry, is equal to C times by X dot minus Y dot. And now we can write the equation of motion for this system. When this mass M is going up, the summation of the force in vertical direction must be equal to the mass times by X double dot. Again, here I should mention that we neglect the weight in the equation of motion and in the free body diagram, because the weight of this mass creates some initial deflection in the spring. So if you plot the free body diagram and write the equation of motion, or the Newton's second law, for this mass, the summation of the force is equal to minus kx minus y, and minus c times by x dot minus y dot, and it must be equal to mx double dot. And if you simplify this equation, you can extract the equation of motion for the system here. Now we can separate the x and y terms. In the left hand side, we we'll have the x terms, which is mx double dot c times by x dot plus k times by x. And in the right hand side, we will move the y terms, which is c times by y dot plus k times by y. So when you move them to the right hand side of the equation, their negative sign will convert into a positive. So this is the equation of motion. As you can see, this is an ODE from order 2 with non-homogeneous term. The non-homogeneous terms include ky plus cy dot, because here we have a damper, we have the derivative of y with respect to time, or the derivative of base excitation with respect to time, and also we have y, which is the base excitation. So if you substitute y from this term according to our initial assumption, that we assume that y is equal to uppercase y times by sine omega t, and substitute here, we will have k times by y, which is k times by uppercase y sine omega t, plus c times by y dot, which y dot is equal to this uppercase y is a constant value. So the derivative of sine omega t is equal to omega cosine omega t. And this is the non-homogeneous term in your equation of motion. Also, you can convert it into, by using the trigonometric identities, you can convert this equation in only a sine function. Here you can see this is the trigonometric identity. You know, in first chapter, I explained that in a harmonic motion, we can write C1 times by sine omega t plus C2 times by cosine omega t, which C1 and C2 are two constant coefficients, times by sine and cosine harmonics. We can write this function in the form of only sine function with an angle phase, which is called alpha, and amplitude A, which A and alpha can be obtained from these equations. A is the square root of C1 squared plus C2 squared, and alpha is the tangent inverse of minus C2 over C1, which C2 and C1 are these coefficients. So by using these trigonometry relations or identities, we can convert this function or the non-homogeneous term in the form of a sine function. So using this form, we will have A times by sine omega t minus alpha, which A is the amplitude. And if you substitute here, you can see that C1 is K times by uppercase Y, and C2 is C omega Y. So instead of C1 and C2 in these two equations, we substitute from the non-homogeneous terms and simplify. So we will have the amplitude, which is this term, and the alpha or angle phase, which is tangent inverse of minus C omega over K. Now we can solve this equation for the non-homogeneous system and obtain the particular solution or the steady state response for this system subjected to a base excitation. The particular response can be considered at uppercase x sine omega t minus alpha minus phi1, which phi1 is the tangent inverse of c omega on k minus m omega squared, and uppercase x, which is the amplitude of the response, can be obtained from this equation. We use the formula extracted in previous chapter. And now we define a new parameter, which is called displacement transmissibility, and or dt, which is the ratio of uppercase x, the amplitude of the response, to the uppercase y, which is the amplitude of the base excitation. And if you substitute and simplify, you can see that the dt or displacement transmissibility can be obtained as a function of Kasai and frequency ratio, which Kasai is the damping ratio and R is the frequency ratio, and R is equal to omega divided by omega n, or the ratio of omega to the omega n. And this omega is the frequency of the base excitation. Again, please pay attention that this omega, this term, is not the natural frequency of the system. This is the frequency of the excitation, and omega n or omega d is the frequency of your system. Now we can simplify the particular response, and also we can write that xpt by using the trigonometric identities. We can write that xpt, the particular response, is equal to x sine omega t minus phi, which phi is the angle phase of the response, and in fact phi is equal to alpha plus phi1, and we can obtain again phi, the angle phase, as a function of psi and r. Again, you can see that the angle phase is a function of the damping ratio and frequency ratio. So when you have the natural frequency of your system and also you have the damping ratio, you can obtain the angle phase, and also you can obtain the amplitude of your response as a function of these two important parameters, because we have the frequency of the excitation, we have the frequency of your system, and the damping ratio. So you can write the response of your system to any type of excitation and any type of loading or a base motion. Okay, any questions so far? Is it clear?
Yes, sir.
Okay. So we can plot the displacement transmissibility versus the frequency ratio, and we can extract some conclusion from these curves. TD, or the displacement transmissibility, is the ratio of uppercase X, the amplitude of the response, to the amplitude of the base excitation, X to Y. And as you can see, this is a function of damping ratio and frequency ratio. So for different value of psi, as you can see here, we have different value for psi or damping ratio. You can plot this parameter versus R. So for example, we assume that psi is equal to 0.05, and then you can plot TD versus R, and it will extract this graph. Or again, you can substitute psi is equal to 0.1, and then you can plot the graph for TD versus R. So these are different graphs for different psi or different damping ratios. And now we can extract some conclusions. The value of TD is unity at R is equal to 0 here at this point, or when we are close to R is equal to 0. You can see that TD is equal to 1. It means that the amplitude of the response is equal to the amplitude of the excitation. And also for this point, you can see that when omega is equal to a square root 2 times by omega n, or omega is approximately equal to 1.4 times by omega n, for all of the value of the damping ratio, again, you can see that the amplitude of the response is equal to the amplitude of the excitation. It means maybe the most popular example for the base excitation is the suspension system in the car. Assume that, for example, in your car, the excitation frequency, or omega, is equal to the omega n, is equal to the frequency of your car, the frequency of the suspension system in your car. So if you pass a bump, for example, with the length of 20 centimeter, the displacement of your car body will be exactly 20 centimeter when omega is equal to omega n. Or when the frequency of the excitation is equal to 1.4 times by the frequency of your suspension system, again, the same amplitude of the bump will be, you can feel exactly in your car when the frequency omega is equal to 1.4 times by omega n. And the frequency omega, or the frequency of the excitation, is directly related to the speed of your car. I mean, by changing the speed of your car, you can change the frequency of the base excitation. In the examples, I will explain sometimes that when you have a moving car, you have a moving vehicle, and it's facing some bumps or some base displacement, you can extract the frequency of the excitation as a function of the speed of your vehicle. So by changing the speed of your car, you can change the amplitude of the response. And usually in a car, we prefer that decrease the amplitude of the response, because when you decrease the amplitude of the response or decrease the x, in fact you are decreasing the motion of your car, and we usually prefer to decrease and vanish the motion of the car versus the motion of the base or the bumps. So this here you can look at this, and for example here, when we are at this area, when omega is more than omega n, we can conclude that x, the uppercase x, or the amplitude of the response, is very low for all of the value of the damping ratio. The next conclusion is for an undamped system. It's an important conclusion that the TD will go to infinity at resonance here when omega is equal to omega n, and when the damping ratio is 0, the TD will go to infinity, and we call it resonance. The value of TD is less than unity for values of r more than a square root of 2 in this area. As I told you, you can see in this area is a preference for us when we want to design a suspension system for a vehicle, because as you can see, the amplitude of the response is less than the amplitude of the excitation. Okay, so this is the preference area of when you want to design a suspension system for a vehicle. But in this area, you can see that the amplitude of the response is more than the amplitude of the excitation. It's like that, for example, when you are passing a bump with, for example, 10 centimeter height, your car will experience a motion of more than 10 centimeters, for example, 20 or 30 centimeters. So you can see for a small bump, your car will start to go up and down more than that bump. And this is due to the frequency is less than the frequency of the excitation. Sorry, the excitation frequency is the less than of the frequency of your system, or omega is less than of omega n. So again, it's up to you. I mean, when you are driving a car, you can, by changing the velocity of your car, you can change the response of your car when you are facing the different bumps and different base excitation, in fact. And here the value of TD is unity for all values of psi, as I told you in the first conclusion. For r less than square root of 2, smaller psi leads to large values of TD. And on the other hand, for r more than square root of 2, the smaller psi leads to smaller values of TD. So when omega is less than a square root of 2 times by omega n, or when we are in this area, you can see that by increasing the damping ratio, the TD is decreased, but in this area, by increasing the damping ratio, TD will decrease. So according to the frequency of the base excitation, you can also control your motion by changing the damping ratio or by changing the damping constant in your system. Another important point, sometimes in your system, you don't need to decrease the amplitude of the response. For example, when you deal with a system, an harvesting system, for example, assume that in one of our projects, in one of my students, for example, we are designing a vibrating system to harvest the energy from the ocean waves. In this case, we need to increase the amplitude of the response. I mean, the ideal case is when X is more than Y. And we prefer, for example, when the length, or sorry, when the height of the wave is 10 centimeter, we prefer that X, the amplitude of the response, be, for example, 20 centimeter. So we should try to design a vibrating system which the frequency of that system must be in this area, or in the other words, the frequency of the excitation, which is in fact the frequency of the ocean waves, must be in fact less than 1.4 times by the frequency of our system. So if we assume that, for example, the omega, the frequency of the ocean waves is, for example, 1 radian per second, we should try to design a system with natural frequency more than 1 divided by 1.4. So this is very important, that you want to decrease your amplitude in the response, or you want to decrease it according to your system. In a car, for example, we prefer to decrease the amplitude of the response, but when we want to harvest the energy from a vibrating system, we usually prefer to increase the amplitude of the response. And finally, the last conclusion, the TD attains a maximum value for Kasai between 0 and 1, or for an underdamped system, when R is equal to Rm, and Rm can be obtained from this equation. So when the frequency to the frequency ratio, sorry, the frequency to the ratio of the frequency to the natural frequency is equal to this value, you can obtain the maximum value for your TD. So in the case, for example, in our project, when we want to design a system for harvesting energy from the ocean waves, we should try to design this Rm for our system, because the frequency of the ocean waves is not in our hand, but the vibrating system that we are designing is up to our calculations. So we can design a system with damping ratio like this Kasai, and by designing this Kasai, we can increase the amplitude of the response for this case when we are in this area. Okay, any question? Is it clear?
No questions, sir.
Okay, so the application of these type of graphs is when you want to design a vibrating system for a real problem in an experience. So you can use these graphs and you can find your preference, and you can, according to your preference, you can find your suitable area for your system, and then you can design the different value, for example, the stiffness, the mass, and the damping constant for your system. Okay, the force transmitted to the base due to the reaction from the spring and damper can be obtained K times by X minus Y plus C X dot minus Y dot. If we refer to the first slide, when we plotted the free body diagram here, in this case, when we plotted the free body diagram, and when the mass m was going up, we had this force which was k times by x minus y, and we have the reaction exactly the same value with the opposite direction, which is again k times by x minus y, which is exerted to the base. And the total force which is transmitted to the base is equal to the summation of these two forces, kx minus y plus cx dot minus y dot. So this is the transmitted force, and now we want to discuss this transmitted force. Here you can see, and we know that the summation of this force is equal to minus mx double dot. In fact, in the first slide, when we wrote the Newton's second law, we had minus k times by x minus y minus c times by x dot minus y dot was equal to mx double dot. So when we multiply that equation with -1, we can extract this term. Now we can substitute because we extracted the x and also we have the y. When you substitute here, you can obtain, because f is equal to minus m times by x double dot, and x is obtained from the particular solution in previous slides. So we will have m times by omega squared times by uppercase x times by sine omega t minus phi. And now we call it ft times by sine omega t. I mean, instead of m times by omega squared times by x, we substitute ft, which is the which is called the amplitude of the transmitted force. And now if we divided it by k times by uppercase y, we can find this relation, and it is called force transmissibility. And again, this is the force which is transmitted to the base, and k times by y, which is the y is the amplitude of the base excitation or base motion, and k is the stiffness of this spring. And this ratio is called force transmissibility. Note that here, if you look at the form of the response and form of this transmitted force, you can see that the transmitted force is in phase with the motion of the mass, or xt, because both of them are function sine omega t minus phi, and x is also sine omega t minus phi. Okay, we continue with some examples. Figure shows a simple model of a motor vehicle that can vibrate in the vertical direction while traveling over a rough road. The vehicle has a mass of 1,200 kilograms, so the mass is 1,000 or 1.2 ton or 1,200 kilogram. The suspension system has a spring constant of 400 kilonewton per meter, so the stiffness is 400 kilonewton per meter, and the damping ratio of psi is equal to 0.5. If the vehicle speed is 20 kilometers per hour, determine the displacement amplitude of the vehicle. Here you can see we have the vehicle speed, which is 20 kilometers per hour, and the vehicle speed in fact is in the horizontal direction. So we can assume this is, as here explained, this is a simplest form of a suspension system, as you can see. And this suspension system is moving with a velocity of 20 kilometers per hour on this rough road. We can assume again that the equation of the curve fitted to this rough road is y times by sine omega t, which this omega will be obtained as a function of this velocity v. And I will show you how we can obtain this. Here, the road surface varies sinusoidally with an amplitude of 0.05 meter and a wavelength of 6 meter. What does it mean? It means that we will have, if you plot this road curve on for x, which x is the displacement, we will have a curve like this, which the wavelength, this length is 6 meter, okay? And the amplitude of this wave or this height is equal to 0.05, which is in fact called the amplitude y, and this is the wavelength, 6 meter. So the form of the road surface, in fact, can be assumed something like this with the wavelength 6 meter, and the height of a wave is about 0.05 meter. And now, according to this data, the velocity of the vehicle, the stiffness of the vehicle, the mass of the vehicle, and also we have the damping ratio. So we want to obtain the displacement of this mass M. In fact, the displacement of this mass M is your response or the response of your vehicle. So let's first calculate the frequency of the excitation. Okay, so the frequency of the base excitation is equal to 2 times by pi times by f, which f is the frequency of the excitation, and this f can be obtained by dividing the velocity of the vehicle by the length of one cycle. As I told you, this length is 6 meter, yes, and we know that the speed of this vehicle is 20 kilometer per hour, and of course we should convert it into meter per second. For this purpose, we should multiply 20 by 1000 and divided it by 3600 to convert from the kilometer per hour to meter per second. Okay, so this is the velocity in meter per second. We know that x is equal to v times by t, which this t in fact is the period of the system, and also we know that the frequency is equal to 1 divided by period. So from here we can conclude that t is equal to x divided by v, which when t is the period, this x is the length of the wave or this 6 meter, and also when f is equal to 1 divided by t, so we can conclude that f is equal to, from here if you substitute, you can conclude that f is equal to the velocity divided by displacement, which we are calculating the frequency of the system, so the displacement in fact is the length of one cycle, which is 6 meter. Now we can calculate f, which is 0.925 hertz. And now we should convert it into radian per second. And omega, which is f times by 2 pi, is 5.8 radian per second. So this is the frequency in radian per second, and this is the frequency in hertz. So you can see this is the frequency of the base excitation. And by changing this velocity, you can change the frequency of the excitation. I mean, if you increase your velocity when you are driving your car, in fact, you are increasing this omega, you are increasing this frequency of the base excitation. So now we have omega, the frequency of the excitation. Also, we can calculate the natural frequency or omega n in the system, and it's equal to a square root of k divided by m, because this is a simple SDOF system. So the frequency of this system is equal to k divided by m, and it's equal to 18.2. And now we can write R, which is the ratio of the omega to the omega n, the frequency ratio. We can calculate this parameter, which is 0.318. Now to calculate the maximum amplitude of the response, we can substitute damping ratio, which is 0.5, and also we have R, we can substitute, and you will see that the response is 0.055. So you can see the amplitude of the base excitation. Let me back to the previous slide. Here is 0.05. So when the height of the base surface is 0.05 meter, or it's about 5 centimeter, you can see that the car, or this mass M, will move in X direction by 5.5 centimeter, or 0.055 meter. So this is the maximum amplitude of the response for this value of the frequency ratio. If you change omega, or in other words, if you change your velocity, you are changing your omega, and conclude here, by changing this velocity, you are changing, in fact, this omega, and by changing the omega, indeed you are changing the frequency ratio, and then you can affect on the uppercase X. So this value can be changed by changing the velocity of your car. Okay, any question for this example? If you don't have any question, we can wrap up this session and continue again on Wednesday.
No question, sir.
Okay. Okay, so if you don't have any question, I will wrap up this session. Thank you for your attention. Please go through to the lecture notes and let me know if you have any question, and we will continue with some examples on Wednesday. Thank you.
Thank you, sir.